So the thing with alcohols is to turn the OH into a good leaving group. How many ways can we do that? We can protonate it, and water's a good leaving group. We can turn it into a bromide. We looked at the tosylate, and so instead of using hydrochloric acid to make a chloride, we can use this thing called Thionyl Chloride. You can see OH there, turned it into an alkyl halide, produces maybe smelly egg smell. So here's the Thionyl Chloride, lone pair of electrons on the oxygen slams into sulfur like it would a carbonyl carbon kind of. And now this thing is kind of charged. This electron can, or this, excuse me, this proton comes off with chloride, and then we have this chloral sulfite ester. And I think this happens real quick, this carbocation, and there we see the SO2 leaving. Now we have a carbocation there. How might we be able to tell that we had a carbocation? Almost looks like a primary carbocation, we don't know. But I imagine this thing has the R and S isomer if it was a asymmetric carbon. So reactions of alcohols, this one should be somewhat familiar because you did this in lab. You took cyclohexanol, some concentrated H2SO4, had your fractional distillation set up, heated it up, and this distilled across. And so this was an E1 event. We know it's E1 because we get the carbocation intermediate and Zeta's product. So here's something new we're going to look at in a second, bimolecular dehydration. We can take alcohols and make ethers with an acid catalyst. It says here if we keep the temperature low, we're going to favor the ether formation. High temperatures, 180 degrees and above, favors the alkene. So here we see the mechanism, protonated OH, makes a good leaving group. It leaves, there's the carbocation, so we know it's unimolecular. And then you can either have solvent. I always like to use the HSO4 minus because then we regenerate the acid catalyst. You can imagine, it doesn't really matter. There's the alkene. So I guess they left us an out. Generally takes place by an E1 mechanism. Rearrangements are possible, and the rate of the reaction follows the same rate as the ease of formation of carbocations. So this would be a tertiary alcohol, secondary alcohol, which this one is, or a primary alcohol. It says primary alcohols like to rearrange. Here's the energy diagram. Little barrier to protonate the OH. Now it's protonated. Rate limiting steps, formation of the carbocation, and then this transition state is base pulling off the hydrogen and those electrons jumping down, forming the alkene. Any questions? As promised, ether formation, which we called bimolecular condensation. Condensation reactions form water. Be sure and use a coaster when you do this. Just kidding. So here is our protonated alcohol. So it looks like we got ethanol, some acid catalyst. So once this is protonated, it becomes the electrophile. Here's the nucleophile, finds that carbon nucleus. This thing finds these electrons, and the water leaves. And if solvent or water comes by and pulls off that proton, here we now have diethyl ether. A protonated alcohol may be attacked by another molecule of the alcohol and undergo SN2 displacement. That's what this is here. This one's protonated. There's the SN2 displacement. And you know it's SN2 because we see no carbocation intermediate. This thing is a concerted process. This is forming a bond. While that bond breaks, no carbocation. So we might call this a bimolecular dehydration. There's the water that leaves. Unique reaction of diols, vicinal diols. So that's OH on adjacent carbons. You remember vicinal and geminal. They underdo these two reactions. Sorry I left this one out of the slideshow. Getting almost too much information. We need to keep moving forward. So here's the vicinal dial. We got an OH and an OH. And under the presence of some H2SO4, we heat it up and we see a ketone form. Pinacol rearrangement. A vicinal dial converts to the ketone pinacolone under acidic conditions. And this is classified as a dehydration since we get a molecule of water out of the starting material. How does this work? Most of our alcohol chemistry goes with protonating the OH. Now this thing's protonated, it becomes a good leaving group. It leaves, and there is a carbocation. What do carbocations like to do? Rearrange. We're gonna see this methyl group here do a methyl shift. Now to me, the question might be why? Because this looks like a tertiary carbocation. This here really looks like a secondary, but anyway, it just must be how nature works. Notice that the OHs are adjacent. If this was a carbon or a hydrogen, you know, we wouldn't be looking at this reaction. Well, this thing is resonance stabilized. This thing can't stabilize itself, but this can, and nature seems to like to do that. If it can delocalize the charge, it's going to delocalize the charge. Those electrons can jump down, so the positive charge is getting delocalized here. Resonance stabilized carbocation. So we just imagine a base coming by, pulling off that proton, and here is the ketone. So we'll have an exciting lab where we make banana oil, where you do a Fischer Esterification. What you do is you take an alcohol, and it's going to be isoamyl alcohol and a carboxylic acid, acetic acid, and some acid catalyst, and you get an ester. Now we can make esters with tosylate esters, sulfate esters. Well, we're going to look at nitrate esters, phosphate esters. So here is the Fischer Esterification. Here's our alcohol, here's our acid. You can see water right there. And so this is kind of like a dehydration. Here's our ester functional group. There's the water. So a Fischer Esterification is reacting an alcohol with a carboxylic acid. Here sulfuric acid is used as the catalyst. So notice an equilibrium arrow. In lab we use a large excess of this for Le Chatelier's principle to slam everything to the other side. Many times you distill off product or something. But it says here, for this reason, the Fischer Esterification is seldom used to prepare esters. It's used to prepare esters all the time in organic chemistry labs, but industrially, if you want to make a lot of ester, industry is going to do something a little different. What might it do differently? So here we see what we'd call an acid chloride. If this was an OH, we'd have the carboxylic acid. So I think reagents like Thionyl Chloride can make the acid chloride. And here you see these things coming together and giving us HCl, but we use this pyridine that kind of soaks up the proton coming off. Notice no equilibrium arrows. It really wants to go to one side. So the esterification reaction achieves better results by reacting the alcohol with an acyl chloride. The reaction is exothermic and produces the corresponding ester in high yields with only HCl as a byproduct. The pyridine neutralizes the HCl. So here is glycerin, also called glycerol, and here's nitric acid. So this kind of looks like an OH group, and so this is a nitrate ester, and we might call this nitroglycerin. Why is the best known nitrate ester nitroglycerin? Do you watch those Western movies? Almost TNT. TNT is trinitrotoluene, which is a little more stable than this. Yeah, let's just look at the, here is a toluene. Let me fix that up. Here's the TNT. So this stuff here, it's very shock sensitive, hard to handle without hurting yourself. It's a liquid. So this can be made, it's a solid, you can drop it. So here's an alcohol, here's phosphoric acid. We see OH and a proton there. So we call this thing a phosphate ester. It has the similar thing going on with a double bonded oxygen, single bonded oxygen, just like very analogous carbonyl carbon. Now we still have OH groups here. We can imagine another alcohol coming by, and now we have this dimethyl phosphate, and here would be trimethyl phosphate. For fun and no prizes, what is the most famous phosphate ester known to mankind? Let me give you a hint. I'm told that out of all the elements, the one that really limits the amount of life on the surface of the earth, you know, most life is carbon-based, right? But carbon isn't the limiting element when it comes to life. There's another element, of course, it's phosphorus. So that's like ATP, right? We're getting close. We're going into biochemistry. So the intro chemistry students just had a quiz, and it says, what is the acronym for the molecule that's in all living organisms? It's 3 letters. There you go, DNA, absolutely. So phosphate esters in DNA. So here's a single strand, but here's a phosphate, and this weird, looks almost like a sugar and hooked up to these base pairs. So at the beginning of this chapter, one of the first things I went over is when you put sodium metal into an alcohol, what do you get? You get the alkoxide ion, and here's an alkyl halide, and so this looks like a SN2 reaction, and here's an ether. So now we've looked at this bimolecular condensation, a way to get an ether. Those are made industrially, just a few, like the diethyl and maybe methyl, dimethyl. We'd call those symmetric ethers, but if you want a non-symmetric ether, like methyl pentyl ether, probably gonna have to do something like this. Ethers can be synthesized by the reaction of an alkoxide ion with primary alkyl halides in what is known as the Williamson ether synthesis. So named reactions might always be a big deal. You got the Fischer Esterification from this chapter, and now you have the Williamson ether synthesis. Here's an important thing, SN2. So you think you want to use a tertiary alkyl halide here? Yes or no? No, you'll get an alkene. You'll have the E2 reaction occur. So for points on a quiz or exam, if you're asked to make an ether by the Williamson ether synthesis, and you have maybe like 2 alcohols, one alcohol you can use your phosphorus tribromide or some means to make a good leaving group like alkyl halide. The other alcohol you're going to react with sodium metal or this sodium hydride. Both of these and alcohol are going to give you the alkoxide ion. The only difference is I believe this might be a little easier to work with, not quite as exothermic as dumping sodium into a beaker of alcohol. If a secondary or tertiary alkyl halide is used, the alkoxide will act as a base and elimination will take place. So all that fun stuff we learned in the fall comes back to cheer us on. You bet you thought I was going to use the word haunt. What is the product formed here? So there is a alkoxide. So this might be a good way to get this ether here. So let's compare and contrast this. So here we might get some alkene, secondary alkyl halide. I should have come up with the example with tertiary, but notice, you know, here's 3-carbon chain, maybe corresponding to a 3-carbon chain there. Here's a 3-carbon chain, maybe corresponding to a 3-carbon chain there. So with the William ether synthesis, you want to choose it so you're using a primary alkyl halide over a secondary or tertiary. Any questions? So we want to be able to do a synthesis. And so here's a starting material. All these little reactions get done. What is our end product? So thionyl chloride, what does that make? Takes the OH and replaces it with what? Alkyl halide. Then this thing gets put into some ether with magnesium, and then what do we get? And I always tell my students, when you see a Grignard reagent, there's the business end of a Grignard reagent. All right, here's a line drawing. Evidently there's a hydrogen there. What do Grignards do with aldehydes? Well, this carbon has a partial positive charge due to the electronegativity of the oxygen. All right, so it looks like we have a 1, 2, 3, 4 carbon chain. 1, 2, 3, 4 carbon chain. And then this is a 1, 2, 3 carbon chain. 1, 2, 3. And then we get this thing is protonated. So we learned that Grignards react with aldehydes to form secondary alcohol. What's the product? So phosphorus tribromide, good brominating agent, turns an alcohol into corresponding alkyl halide. Then we're gonna get a Grignard again. So what is deuterium oxide? You're not gonna find deuterium on that periodic table. Deuterium is an isotope of what element? Water. Yeah, we call this heavy water. And Grignard reagents we form here. You know, I can imagine this. What I tell students, there's the business end of a Grignard. So this here is an acid-base reaction. I could have just as easily put water here, and then we just get the alkane. So this is a review of some of the concepts on these first 2 chapters. Alcohol chapter, reactions of alcohol. Any questions?